We proceed with alkyl halides and we are going to consider Sn2 reaction. Now, when we are talking of course of alkyl halides, we've got an alkyl that is bonded to an halogen. And so I can simply write that as, let's say we have got, I'll give a very simple example. We have got a methyl and then you have got bromine attached at one end, right? So what is going to happen is that a reaction can happen. Let's say this bromine is more electronegative than the carbon. So this bond is going to be broken in such a way that this bond that we are able to see here, the two electrons are going to go on the more electronegative atom. And so what we are going to get is a carbon with just attachment of those. And then we are going to have a bromine with a negative charge. And then okay, this one is going to remain with a positive charge because it has lost electrons. And this one is going to have a lone pair of electrons that has come from the bond that has been broken. So this is called nucleophilic. It can be a substitution or elimination, right? It can either be a substitution or elimination. Actually, when you have got something that is coming to attach, it eliminates the one which is there. Okay, so since I have just a bond that has been broken, to show that necessary, yes, indeed, it is a nucleophilic substitution or elimination. Let's say we have got a carbon which is bonded to, we can just put anything as long, okay, we can have a bromine here, we can have another compound there, another compound here. Okay, and then we are reacting this with another substance, let's say a nucleophile. Now a nucleophile has got electrons, a lone pair of electrons, so it's going to have a negative charge. Now we say uh, this compound, the bromine, is more electronegative than carbon, then it's going to have a partial positive charge, right? I mean partial negative charge because it's more electronegative, and the carbon is going to have a partial negative charge. So since this nucleophile is negative and the carbon is also negative, what is going to happen in this reaction is that these two lone pairs of electrons are going to be able to attack the carbon which is negatively charged. And what we are going to see is that this bond is going to be broken, taking the two electrons to the bromine. And so we are going to have a carbon bonded like that, and then we are going to have an attachment of a nucleophile. Then the bromine is going to be alone with a lone pair of electrons, and then it's going to have a negative charge. So such a reaction which we are able to see like this one is called a nucleophilic substitution or elimination. Okay. Now I can simplify this by saying we have got a nucleophile which is attacking the alkyl halide. So I'll say we have got an alkyl group R which is attached to an halide. Let me give it X. That is a halide. It can be any halogen: chlorine, bromine, fluorine, iodine. So I've got an alkyl bonded to an halogen. This is reacting with a nucleophile, and this is going to form what? So these two lone pairs of electrons we can see on the nucleophile attacks the alkyl group, and then this bond is going to break, taking the electrons on that one. So we're going to have R now attached to the nucleophile, and then we are going to have now X alone with a lone pair, and then it's going to have a negative charge. So we can write the rate expression for this reaction. The rate of this reaction is given by the rate constant, and then we look at the reactants. We have got R bonded to X, and then we have got the nucleophile. So this is the rate expression for this reaction. And so we can see that the coefficient here is a 1, the coefficient here is a 1. So you have got power 1, power 1. So we can conclude this is a second order reaction. Why? Because this is this reaction, we have got two reactants which are coming together. Okay, we have got this reactant and this reactant coming together. Or we can say this is a biomolecular reaction. That is the molecularity of this reaction. It is bimolecular, meaning that you only have two things which are reacting. So an Sn2 reaction is a bimolecular reaction. Now the S here just stands for substitution. The N is representing nucleophilic, and then the 2 is the one which is representing bimolecular. So this is it about Sn2 reactions. Now let's get to understand them a bit in detail. So just from the one we've written here, the rate law expression, it means if I get to double the concentration of the nucleophile and then I double the concentration of the alkyl halide, then the rate is going to increase by a factor of 4. If I double the concentration of the alkyl halide and then I triple the concentration of the nucleophile, then the rate is going to increase by a factor of 6. So this is about Sn2 reactions. So let's get to look at them in a bit of details. We can look at the reaction mechanism of an Sn2 reaction. Like a mechanism is simply a series of steps that get to happen for that reaction to be complete. Alright, so let's say we've been given this compound. We have got a carbon, and this is a chiral carbon, meaning that it's bonded to 4 different things. So let's say it's bonded to a bromine atom, and then it is bonded, let's say, to a methyl. Now I'm also going to show the stereochemistry, meaning that this atom which is bonded this side is coming towards us, so it is coming from the board. So this is a methyl, and then let's also attach an hydroxide. Okay, can I just change this so that I put this one which is going in the board as hydrogen, and then now I can have a methyl going in the board. This one is coming towards us, so the methyl is going in the board, carbon bonded to 3 hydrogens. And then we are going to have also another one which is coming, which is parallel to the board. Right, let's say that is an ethyl group, CH2, and then CH3. Okay, this is the compound that we have. We can see that this carbon which is here is what? Is a chiral carbon. Why are we saying chiral? Because it's bonded to 4 different things. We've got this atom going in the board, this one out of the board, and then these two are parallel to the board, like they go in these directions, or they're on the surface of the board, like that we can say. Okay, so when we get to bring an electrophile to attack this group, an example of a nucleophile attacking this group. A nucleophile is the one which attacks the atoms. So I can give an hydroxide. Now we know that an hydroxide has got a negative charge on the oxygen, like that, because oxygen has got lone pairs of electrons. This is going to have 3 lone pairs of electrons there. So when this one gets to do attack, it is going to attack, mostly it attacks from the behind of the bromine, all right, from the behind of the halogen. So this one is going to attack from the behind of the halogen, like that. So it always attack, the nucleophile will always attack 180 degrees from where the halogen is. That one, we need to take note of that. Okay, so what is going to happen when that happens is that you are going to have faced a transition state, a state when the reaction is not fully complete. Okay, the reaction is not fully complete. Now this compound that you are able to see here, what would be the name? Now you can see we have got this group. Let's number this. Okay, so we have got, of course, the bromine has got higher priority, so when you are numbering, This is going to be carbon number 1, this is going to be carbon number 2, this is going to be carbon number 3, this is going to be carbon number 4. Okay, like that. And so when you are numbering, you get to give priority to groups of higher priority. Of course, we have got 4 carbons of sin. So this one, we're going to give it position number 1 because it has got higher priority. And then we're going to give this one because it has got higher priority, and then this one. Now, the hydrogen, we're going to fix it. We'll not give it any number. That is the 4th group. So you can see that this is going in this direction. 1, 2, 3. So what direction is this? This is a clockwise direction. So this will give it the symbol S. Okay. So this is going to be, the name is going to, so if the groups were going like this, we would have given it a different name, right? So this one, we are going to name it as S because of how the groups are moving in priority. This is going to be S. This, we've seen that at carbon number 2 I've got a bromine, so 2 bromo. And then we are going to have what? 4 carbons, that is butane. Okay, so that is the name. That's the name. Okay, S2 bromobutane. The S is just representing how the atoms are arranged in space, in the direction. Now, when this OH gets to attack the carbon which is on the middle there, what are we going to be able to see? So before the final product, we are going to have the transition state. Okay, the state when we have got this bond just starting to form with this compound, right? So we're going to see the OH, I'm going to put it this side, right? And then we are going to just show dotted lines because the bond is necessarily not formed. And then the bromine, that is the halogen, is supposed to be displaced. Okay, when this one is attacking, this bond is supposed to be released like that. It's supposed to be broken. And so we are going to see this. I'm putted we've dotted the lines. Why? Because one bond is about to be formed, one bond is about to be broken. And then we have got an hydrogen. We also have a methyl, and then we have got an ethyl. So this is what we call the transition state before the final product is formed. And then from the transition state, now what we are going to see is this bond is now going to be fully broken, and then this bond is now going to be able to attach there, and that will be now the final product. Okay, so this will continue. Then we are going to have a carbon, then we are going to have the hydrogen still coming towards us, and then we have got the methyl, which is going in the board, and then we have got the CH2, CH3, which is on the surface of the board, and then the OH, which is like that. And then we are going to have now the Br, which has been displaced. So this is the reaction mechanism that gets to happen, right? So the first stage, you have got the nucleophile, which attacks the alkyl halide at 180 degrees away from the departing hydrocarbon. That's the first stage. You have got the attacking there 180 degrees. Okay, so we are going to have partially the bond being broken and partially the bond being formed. And then what happens after then? The stereochemistry at carbon is inverted as a carbon to OH bond forms fully. Alright, this carbon to OH bond now forms fully, and the bromine ion departs, this one which has been released here. Okay, so this is the reaction mechanism for an Sn2 reaction. So basically this is what we are going to be able to see. Now the rate of the reaction is going to be affected by a lot of things. One of the things that affects the rate of an Sn2 reaction is called steric factor. Okay, so let's consider what steric factor is and how does it affect the rate of an Sn2 reaction. So for an Sn2 reaction, the nucleophile is going to approach the electrophile carbon at 180 degrees as we have seen. Okay, now the rate of the reaction is going to decrease as the steric factor or the steric effect, can use effect, as the steric effects of the electrophile increases. Now what is steric effect? Steric effect just describes the atoms or the groups which are bonded to the carbon. So if you have got this carbon, it only has hydrogens like this. Then you have got a bromine. When you have got the OH group coming to attack, it will be much easier than when you have got this same OH group now coming to attack something. Let's say we have got a carbon here, you have got a methyl, you have got a methyl, you have got a methyl, and then you have got a bromine. Why is it going to be very difficult to be able to attack? So it will be very difficult to be able to penetrate these atoms because they've got a lot of electrons, and remember it is a lone pair of electrons here which is going to go in that direction to attack. So there will be more like a repulsion on the electrons which are on this compound with these electrons which are on the nucleophile. So because of that repulsion, it will be very difficult for you to be able to attack that carbon which is on the middle. And so here the rate is reduced, okay, because of increased steric factor. So increased steric factor, just look at the groups which are attached to that compound, if there are many or there are bigger groups. Right now here you only have you just have hydrogens, very small. In other words, you are shielding the nucleus of the carbon because of these groups. Remember the way, if you get to show the way these groups are, you're going to have a carbon and then you have got a carbon from the methyl, okay, this carbon here, and it is attached to 3 hydrogen. You are going to have an hydrogen and hydrogen and hydrogen there. Then you have got another carbon which is this one, which is also attached to 3 hydrogens. So this is the other carbon attached like that, attached to that, like that, and then like that. You have got again another carbon attached like that, again another hydrogen like that. So there is more like this atom is being shielded or it is being protected. That is what we call the steric effect. We know not factor, steric effect, also called steric hindrance. So there is a greater hindrance. So when you have got that, the rate of an Sn2 reaction is going to be reduced.